These are some examples of the products that these guys have all developed and are now scaling up at our plant up in San Francisco Bay. And when we talk about concrete's about 80% what we call aggregate. So some of it's fine aggregate, like this sand here. These are all produced with our process. This is pure calcium carbonate, which is 44% by mass CO2 that we've captured. It's now in the crystalline state as CO3. This is an example of a coarse aggregate or a gravel, which is also pure calcium carbonate, 44% by mass CO2, now permanently sequestered in the crystalline state. And that makes up about 80% of concrete. So this is a test cylinder of concrete that we use for mechanical testing. And when it breaks, you see the fractured surface, and you can see the white. That is the sequestered CO2 rock that's been broken in the matrix. So if you were to cut it in half with a saw, you would see that about 80% of the mass of the concrete is fine and coarse aggregate.
Can you hold that right back up again? Sorry.
Do you want me to tap the focus? Are you okay?
Yeah, bring it down just a little bit. Okay, great, thank you.
You got some real sound effects there.
Yeah.
And just make sure you're still talking right into the lens. And then you have that last one, is that right?
Yeah, we make many variations. For example, here, this could be something that we didn't make pure calcium carbonate. Sometimes when we dissolve the materials from which we get our calcium, we have a byproduct, which can also be put in concrete, or it can take up some of the mass of this. So when we formulate it, it looks like a milkshake. And we can mix anything in with it, and it'll still go ahead and form the final product. Call that a composite material.
Okay. And then on that, I'm going to do close-ups of the same, what you just did, so we know you picked that up. And you had it out here a little bit further. Okay, great. And we'll switch back to that one.
And Brent, in the long run, how much of the synthetic limestone do you think will be used for sand and how much for aggregate?
Well, a typical yard of concrete might have 600 pounds of Portland cement in it, about 1,200 pounds of sand, and about 1,800 pounds of gravel. So that's 3,000 pounds of aggregate, meaning both fine and coarse aggregate. And the whole yard might weigh up around 2 tons. You know, these are just approximations. Sometimes you'll put a lot more cement in for various structural reasons. Sometimes you'll put less cement in and more sand. There's any number of variations of concrete mixes. Then there's also mortar, which is important, and it doesn't have any coarse aggregate in it. It's just sand and cement. So you can see a lot of different things. 30% of the concrete market is pre-formed, you know, pipes, things like that. And they have different requirements than a ready mix that you're sending out in a truck and has to be poured very quickly before it's set.
And then, since you can make custom densities and custom hardnesses, ultimately, do you think most rock will end up being synthetic like this?
Well, it opens a new possibility as opposed to something you're digging out of the ground. As a manufactured product, you can control the specifications as tightly as you want. So there are specialty rocks, like for example, all multi-story buildings that have concrete floors use what's called lightweight concrete. You know, so it's 2/3 the density of regular concrete. And that allows you to have a lower load. So a bridge, tall building, a parking structure, all these things are using lightweight concrete, which you achieve with lightweight aggregate. So normal aggregate might be 150 pounds per cubic foot, whereas a lightweight might be 90 pounds or less per cubic foot. So that affects the mass of the final concrete. Another really interesting application that Kate has worked on is called internal curing, where the aggregate can hold on to a lot of water, which it slowly bleeds out over time while it's curing. And this reduces cracking and shrinkage, which on a bridge deck is huge. You know, it's very important. Other applications that we've developed are biomimetic applications. One of the tools over here is a solar reflectometer. And working with Lawrence Berkeley Lab a few years ago, we did a lot of work and realized that what we make, because it's very similar to the minerals in shells, like pearl, it's highly reflective, which today there's great interest in the urban heat island in cities. And our white materials are more reflective than the most reflective materials available today. So the Smart Surfaces Coalition is really pushing Blue Planet formulations, for parking lots, panels on this side of buildings. In addition, we're working with the roofing manufacturers, coating granules that go in roofing materials. And we even have colors that Sung-Hee has developed by mimicking the transition metals in shells and things like that.
Wow.
That are highly reflective. So to have a red that is, I don't know, what would be a number, Sung-Hee? What's a good reflectance number for one of our reds versus
40 to between 40 and 50.
in the
It could be low as 30%, but compared to regular ones, which are around 10%, 20%,
Yeah.
these are much higher than
yeah.
regular.
And it's biomimetic. You see a shell in the intertidal zone at noon and it's subaerially exposed in the sun. And you've got your hat on with your SP, 50, and it's a cold-blooded animal, and it's fine because it has a natural cool roof. And in the tropics, they use conch shells for shingles. They don't know why they do that, but it's because it's much cooler, because it reflects the heat instead of absorbing it.
So it sounds like ultimately in some number of decades, most rock construction materials will be synthetic rock.
It could be.
And how long do you think that would take?
Well, I think we're already seeing a shortage of quarries, not just in Europe and the United States and Japan. I mean, in Japan, they'll rent a rice field for 10 years, take out the rice field, dig down 30 feet, get all the rock out, put the rice back on, and the farmer comes back. I mean, they don't have anywhere to dig for rock. And generally, you can't, if you go to Singapore, they don't have any rock. Florida doesn't have any rock. But there are places like Edmonton, Alberta, where they've got plenty of rock. So like we were talking about earlier, in the Middle East, they don't have any sand because it's all aeolian sand, wind-blown sand that's too fine for these purposes because it has very high surface area. So people around the world are resorting to mechanical production of sand, which means, quarry granite, put it through a machine, use a lot of energy to break it up.
Right.
So it'll initially be just an economic choice, between manufactured sand, manufactured aggregate from mines, in having what we call an urban quarry. So within the urban area, you're actually in a circular economy fashion reusing all the local materials, which is much more appealing than bringing in rock from increasingly longer distances, because the economics of the whole rock industry are really just about transportation. It's not about how much it costs to dig rock out of the ground and wash it off and sort it. It's about how far do you have to transport it
Right.
to the site. And if you're already in the center, in the urban area, that's the biggest delta you can have. And that'll be a key part of the adoption.
Now, for construction, the high quality, the controlled quality that you can produce, how much advantage does that give you, or does that give to the user, to the construction company, compared to natural rock?
Well,
Or I guess
so if you're building, say,
what's your price benefit?
yeah, well, if you're building a multi-story building, your biggest issue is staging and time. So you want to be able to put a floor up every day or two and have the concrete come in and set. So, that's going to affect the amount of Portland cement you put in, the type of concrete you make, and to get a high quality concrete that also is going to be cured in a short period of time so you can keep the construction going is, for example, one of many, many variables that would be taken into consideration in a mixed design. I think the key is having the ability to engineer it. Because when you go out to a quarry, you get what you get. and you have to work around that. So it's a total new way of thinking for the concrete people. Normally, they have to adapt to whatever Mother Nature gives us. And what that typically means is you put way more Portland cement in the concrete than you need to make up for the variability that is inherent in natural rock. So if that goes away, or you can ask the question, well, how would you like the rock? Well, that's a whole new thing. They've never had that option before. It's someone was making an analogy to cultured meat today. And we're trying to make meat taste like chicken or whatever. How about just making up some kind of meat that's the best tasting meat there is? Nobody's doing that. They're trying to imitate, natural meat. And this is different. This is, okay, we're trying to make, for example, concrete is usually seen as the villain. In any structure, any project, it's the main building material. It's also the largest carbon footprint associated with it. But now this is different. The more concrete you use, the more carbon you're sequestering. So the more concrete, the better for the CO2. And that's not the way we've all been taught, right? That's very counter to that idea. And it takes you back to pre-industrial structures before steel was available. Because concrete is only strong in compression. It's almost worthless in tension, torsion, and flexure. It's a linear elastic, brittle material. And hence the rise of steel. But steel wasn't around 200 years ago, and you can find many structures hundreds of years old that had no steel in them, and they're designed differently, and they're taking advantage of the compressive strength of stone and concrete. Like a chalk stone and an arch, that kind of thing. And so we're working with architects to think about pre-industrial structures. We're using more concrete. Like the pyramids, those are concrete. Those weren't slaves with Bronze Age tools making those things and moving them up. They were pouring concrete in place up on the pyramids. So, they fit together like this, right? That wasn't carved. And they had no steel. They had no, wood was used in some structures, but it didn't last very long. There are theoreticians who've looked at the Tower of Babel and thought about its height based on what was known about its angle. And have, calculated that could have only been done with bamboo rebar. But starting to rethink the way we think about concrete and think about it differently. But think about it also as a storage site in the built environment for our CO2.
Great. Yeah, thank you.
Wow. That statement that you made just now that concrete's always been the villain is an excellent soundbite, I think. Yeah, I think we're good, yeah?
Yeah, that's good. Maybe we'll let him get back to it. But I think when I look into the future, and for clothes, we used to use whatever skins were available, and eventually we figured out how to weave and make synthetic fabrics and stuff like that. And with construction, it doesn't make any sense that we would depend on natural fabrics when we can fabricate